Hello again. We're continuing our discussion of limits of functions. We talked about determining whether a function is continuous or not. Now we're going to talk about whether a function is differentiable or not. Basically, whether the derivative exists everywhere, not just the function. Being differentiable at a point means, let's look at the definition of the derivative here. You remember this from chapter 2. The derivative of f of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So a function is differentiable at a certain point if I can plug x, that certain x, into that same function and that limit actually exists. Alternatively, you can show this. So f of x minus f of the x you're trying to plug in on top over x minus that x on the bottom to show that exists. So we need to know both of those. So a function is differentiable everywhere if it's differentiable for all of those x's. And you know functions that are differentiable everywhere, like polynomials and sine and cosine. All right, but the function has to be basically continuous at the point. It has to have no sharp points, and it has to have a tangent line that is not vertical. Okay, so here's some examples of things that would not be differentiable. All right, here's a situation where the function isn't continuous, so it would not be differentiable at x equals 1. Here's an example of a function with a sharp point, so that would not be differentiable at x equals 1. It would be continuous, but not differentiable. And then here's a function where there is a tangent line, a vertical tangent line at x equals 0, so that is not differentiable at x equals 0. All right, so first type of question I can ask you is to determine whether a function is differentiable or not. So if I look at each piece, well, 0 is differentiable and root x is differentiable. So let's see if it's continuous at x equals 0. Does the limit exist? Well, when I look at the left-hand limit and I look at the right-hand limit, they're both equal to 0. So the limit exists. The function exists at x equals 0 and is equal to 0. So the limit exists, the function exists, they're both equal to 0, so the function is continuous at x equals 0. So that's the first part. Now I need to check for differentiability. First, check at x equals 0. Well, the left-hand limit, if I plug 0 into that definition of the derivative, then I get 0 over h, which is 0. The right-hand limit, if I look at that, I'm looking at the second piece, the root x. So what I'm going to get is 0 plus h to the 1/2 minus 0 to the 1/2, and that gets me h to the 1/2 over h, which is 1 over h to the 1/2. And that is undefined when I try and plug in h into that. So this function is not differentiable at x equals 0. All right, here's another example. And again, I'm going to give you a situation where I'm telling you it's differentiable, but we're missing some constants b and c, and we need to figure out what the values of those constants are. So let's make sure that it's continuous. First of all, the left-hand limit and the right-hand limit need to be equal as x approaches 2, since that's where the break is in the function. So if I replace x with 2 in the first piece, I get 4 plus 2b plus c, and if I replace 2 in the second piece, I get just 12. What that means is 2b plus c has to equal 8. So there's the first equation in my system. Now we're going to check for differentiability. Okay, if I look at the left-hand limit of that derivative function, then I've got f of 2 plus h minus f of 2 all over h. Replace f of 2 plus h with that first piece, replacing every x with 2 plus h. That's kind of messy, but that's what I have to do. And that gives me that long mess right there. So let's see if I can subtract some things out. I can subtract out, 3 pairs of things that are being added and subtracted. So those are gone, and I'm left with 4h plus h squared plus bh all over h. I can simplify that by dividing every single term by h, and I get 4 plus h plus b with nothing in the denominator except a 1. So I get 4 plus b. Okay, so that is the limit of the derivative of the left-hand piece. Now I need to look at the right-hand piece. That's actually going to be a lot easier. So if I replace x in the second piece with 2 plus h, I get all of that. and things cancel out again, and I'm left with just 7h over h, which is just 7. So I get 7 as my right-hand limit. So 4 plus b has to equal 7 in order for this function to be differentiable. So there's my system. And if I solve it, I get that b is equal to 3 and c is equal to 2. Those are the values of b and c that would guarantee that this function is not only continuous, but differentiable. All right, so that's today's lesson. If you have any questions, please let me know, and I will see you tomorrow.